We've done one example of applying Newton's second law, and I would like to do another. One example that comes up from time to time is the idea of pushing on a box that's pushing on a box. So I'm going to take these two boxes, put them right up next to each other, and then we'll have a person pushing against one box that's pushing against another. We're going to give this one a mass of 100 kilograms, and we'll give this one a mass of 50 kilograms. We can push with a force of, let's say, 450 newtons. And we want to know, we'd like to find the acceleration, and we'd like to find the contact force between the boxes. So first, I'm going to start with a free body diagram. I'm going to call this block 1. Call this one block 2. If I draw a free body diagram for block 1, it will look like this. I will have gravity going down. I will have a normal force going up. I am pushing this thing to the right, which I will call my push force, and then block 2 is up against it, so I'm going to call this a contact force. That would be my free body diagram for block 1. Now I do like to have an axis in here, so I'm going to call upward my positive y, to the right my positive x. I don't want to do anything funny with my axis at all on this because my motion is horizontal, so having a horizontal axis makes sense. For block 2, I'm going to get an M2G going down, an N2 going up. Here's that contact force again, and I'm actually going to relabel this. I'm going to call this thing C on 1 due to 2. This one's going to be C on 2 due to 1. And there's not a push force on this equation, or on this free body diagram, because the person is not actually pushing against block number 2. That's an after effect. So I'm going to draw my axis in this one. My motion's horizontal, so horizontal would make for a good x-axis. There's a y-axis. And I have my two free body diagrams. Now I don't really care what's going on in the y direction. I don't. My acceleration is going to be completely horizontal. This thing's not moving up and down. So I don't even really care about the y thing. What I do care about is what's going on in the x direction. So for block 1, my sum of forces in the x direction, I've got that push force to the right, and I know that's my 450 newtons, so I don't have to write that one in red. That's a known quantity. Minus the contact force is equal to mass 1 times acceleration. This is good, except there are two unknowns, C12 and M1A, or just A. I don't really have anything else I can do with this one, so I'm going to try looking at box number 2. Sum of forces in the x direction here, I have just C12, or C21, but they're equal. I should point that out. This and this will make a third law pair, so they are equal and opposite. I don't need to put any negatives or anything like that as far as the magnitudes, because I'm saying if this is a 50 Newton force to the left, this is a 50 Newton force to the right, this will come out to be negative just because it's pointing in the negative direction. So I'm going to plug in a positive 50, but I'm subtracting it. Here's M2A. Now a couple of things. These two have the same acceleration. So these two forces are equal. And these two accelerations are equal, because if the one moves, then the other one will. So I just have this system of two equations with two unknowns. I'm going to take these two equations and just add them. Over here I get P plus C21 minus C21. They're equal, so I'm just going to call them the same thing. Equals M1A plus M2A. So I just added all the stuff on the left, all the stuff on the right. Now I can start canceling. Those two cancel. That leaves me with push force equals, and I'm going to factor out an A, so that leaves me M1 plus M2 times the acceleration. My acceleration is going to be push force over M1 plus M2, 450 newtons over 100 kilograms plus 50 kilograms. That's 150, 450 over 150 is 3. I'm going to get an acceleration of 3 meters per second squared. I also was asked to find this contact force. So I'm going to do that. Equation 2 right here seems like a really nice one to use, because it says my contact force is equal to M2 times the acceleration, which I now know. So 50 kilograms times 3 meters per second squared gives me a contact force of 150 newtons. Mass 2, block 2, is a third of the total mass, so it ends up feeling a third of the total force. So this checks out. There is another way that we can do this same problem, and it looks like this. What if I said, I'm going to take this whole system and treat it as one? I can draw a free body diagram for the two blocks together, so the system I'm looking at, I'm effectively pushing against one block that looks like that. I'm going to get my push force to the right, my normal force, and my M times G. I'm going to put a capital M to mean the total mass. X, Y. Again, don't really care what's going on in Y, but in the X direction I can say my sum of forces is, I've got just the push force equals mass times acceleration. So my acceleration is the push force divided by the total mass, 450 newtons over 150 kilograms equals 3 meters per second squared. I get the same acceleration, and if you look, I even get the same equation, right? I have right here, acceleration is push over mass total, acceleration is push over mass total. It comes out the same way. The downside to doing this way, because it sure does look like, man, that's faster. The downside to doing this, I've treated the whole thing as one system, which eliminates any internal forces. The second part of this question was asking for that contact force, which is an internal force. So if I want to solve the second part of this problem, I'm still going to have to do a free body diagram for block 2. It'll look exactly the same as it did back here. So there's not extra work. The only reason to really avoid The other method where I combine it into one system is I'm changing the definition of my system halfway through, which is fine if I'm really conscious of it. If I am doing problems and I am either in a hurry or I am, I don't know, maybe not operating at 100%, then it might be a nice thing to do all my definitions right up front and say, this is what my system is. I can draw some free body diagrams. I'm not going to have to break up this system again. I can do this math right here on this screen. Like, that's not particularly rough. If I want to go about this and say, I don't need to jump right into the problem, I can take an extra few seconds and kind of think about how to make this easiest. This will work really well. It finds your acceleration really quickly. But then I do have to have the presence of mind to say, oh yeah, now I have to split this system up again and just use something that has block 2 only. So, not a big deal. Either way, 2 different methods of solving the same problem that come out to be exactly equivalent.